Space weather. The variable conditions in space that can influence our lives. In order to protect the people and systems that might be at risk, we needed to understand the causes and the effects of space weather. Main source of space weather in our solar system is the Sun. Here is the Earth and its position in the green zone that makes it livable. The Earth is rotating on its axis, creating day and night. On the one side we have day, while on the other side the Sun is not visible and we have night. The season that we are experiencing is caused in part by the amount of direct sunlight we are getting, which is influenced by the Earth's tilt on its axis as it cruises around the Sun in its orbit. Geomagnetic storm. A major disturbance of Earth's magnetosphere that occurs when there is a very efficient exchange of energy from the solar wind into the space environment surrounding Earth. It occurs at the day side of the magnetosphere. Storms result in intense currents in the magnetosphere, changes in the radiation belts, and in the ionosphere. They create beautiful aurora. They can disrupt navigation systems and create harmful geomagnetic-induced currents in the power grid and pipelines. Geomagnetic storms are classified in a 5-level scale according to the risk. G5 extreme, 4 days per cycle. Blackouts, widespread voltage control problems. Spacecraft operations may experience extensive surface charging, problems with orientation, uplink or downlink, tracking satellites. Satellite navigation may be degraded for days. Aurora has been seen in low latitudes. G4, severe, 60 days per solar cycle. Possible widespread voltage control problems. Spacecraft operations may experience tracking and orientation problems. High-frequency radio propagation sporadic. Satellite navigation degraded for hours. G3, strong, 130 days per solar cycle. Surface charging may occur on satellite components. Low-frequency radio navigation problems. G2, moderate, 360 days per solar cycle. High-latitude power systems may experience voltage alarms. Finally, transformer damage. G1, minor, 900 days per cycle. Weak power grid fluctuations, migrating satellite operations, migratory animals are affected. The events that cause geomagnetic storms. Solar wind. A solar wind continuously flows outward from the Sun and consists mainly of protons and electrons in the state of plasma. Different regions on the Sun produce solar wind of different speeds and densities. Coronal holes produce a solar wind of high speed. The north and south poles of the Sun have large coronal holes, bringing geomagnetic storms. In the equatorial plane, we have a slow-speed wind, bringing calm space weather. Coronal holes. They appear as dark areas in the solar corona because they're cooler, less dense regions than the surrounding plasma. Persistent coronal holes are long-lasting sources for high-speed solar wind streams. Strong co-rotating interaction regions and the faster coronal hole high-speed stream can impact Earth's magnetosphere enough to cause periods of geomagnetic storming that buffer Earth for many days. Coronal mass ejections. Large expulsions of plasma and magnetic field from the Sun's corona. They can eject billions of tons of coronal material and carry an embedded magnetic field. They travel outward from the Sun. The fastest Earth-directed coronal mass ejection can reach our planet in some hours. The slower can take several days to arrive. The increased radiation storm can provide 15 to 60 minutes of warning of shock arrival at Earth. Solar flares. Large eruptions of electromagnetic radiation from the Sun lasting from minutes to hours. The sudden outburst of electromagnetic energy travels at the speed of light. Radio waves that interact with electrons and lose energy due to the more frequent collisions can cause high-frequency radio signals to become degraded or completely absorbed. Solar radiation storm occurs when a large-scale magnetic eruption accelerates charged particles in the solar atmosphere. The protons can traverse in 10 seconds, reaching our planet. They penetrate the magnetosphere that shields Earth, arriving near the north and south poles. Solar radiation storms cause important impacts. When energetic protons collide with satellites or humans in space, they can penetrate deep into the object that they collide with and cause damage to electronic circuits or biological DNA. Passengers and crew in high-flying aircraft at high latitudes may be exposed to radiation risk. The energetic protons collide with the atmosphere. They ionize the atoms and molecules, thus creating free electrons. These electrons create a layer near the bottom of the ionosphere atmosphere that can absorb high-frequency radio waves, making radio communication difficult or impossible. Solar radiation storms are classified using a scale from S1 to S5. S5, extreme, one event per solar cycle. Unavoidable high radiation hazard to astronauts, passengers and crew in high-flying aircraft at high latitudes may be exposed to radiation risk. Satellites may be rendered useless. Memory impacts can cause loss of control. Serious noise in image data, star trackers may be unable to locate sources. Permanent damage to solar panels. Complete blackout of high-frequency communications. Errors to navigation operations. S4, severe, 3 events per cycle. Unavoidable radiation hazard to astronauts. Satellites may experience memory device problems, noise on imaging systems, star tracker problems, blackout of high-frequency radio communications. S3, strong, 10 events per cycle. Radiation hazard avoidance recommended for astronauts. Concerning satellite operations, slight reduction of efficiency in solar panel. Finally, degraded high-frequency radio propagation through the polar regions. S2, moderate, 25 events per cycle. Passengers and crew in high-flying aircraft at high latitudes may be exposed to elevated radiation risk. Satellite operations may experience infrequent single-event upsets. S1, minor, 50 events per solar cycle. Minor impacts on high-frequency radio in polar regions. Sunspots. Dark areas that become apparent under the sun's photosphere as a result of intense magnetic flux pushing up from further within the solar interior. Sunspots are sources of significant space weather events such as solar flares, coronal mass ejections, radiation storms, radio bursts. Aurora. Aurora is the result of electrons colliding within the upper reaches of Earth's atmosphere. During major geomagnetic storms, the accelerated electrons follow the magnetic field of Earth down to the polar regions, where they collide with oxygen and nitrogen atoms and molecules in Earth's upper atmosphere. In these collisions, the electrons transfer their energy to the atmosphere, thus exciting atoms and molecules to higher energy states. When they relax back down to lower energy states, they release their energy in the form of light. Radiation belts. Radiation belts are regions of enhanced populations of energetic electrons and protons by the energetic electrons and protons makes this a very harsh region for satellites. The energetic particles that compromise the radiation belts can be hazardous for satellites and astronauts. High-energy radiation belt protons and high-energy galactic cosmic rays can alter the state of sensitive electronic devices on satellites, resulting in computer errors or failures. When NEV electrons precipitate into Earth's upper atmosphere, they can deplete ozone and affect the chemical processes in the atmosphere. Ionospheric scintillation. Ionospheric scintillation is the rapid modification of radio waves caused by small-scale structures in the ionosphere. Severe scintillation conditions can prevent a GPS receiver from locking on to the signal and can make it impossible to calculate the position. Scintillation of radio waves impacts the power and phase of the radio signal. Galactic cosmic rays. Galactic cosmic rays are a highly energetic background source of energetic particles that bombard Earth. They originate outside the solar system and are formed by explosive events, such as supernova. These particles pose little threat to humans and systems on the ground. The Earth's own magnetic field also works to protect Earth from these particles, but providing little to no protection near the polar regions. These shower of particles can result in increased radiation exposures for aircrew and passengers at high latitudes and altitudes. These particles sometimes deposit enough energy to result in errors or damage in spacecraft electronics and systems. Space weather impacts on climate. The most important impact that the Sun has on Earth is from the brightness or irradiance. Energetic particles penetrate into the atmosphere and change the chemical constituents. These changes can have long-lasting consequences in the upper and middle atmosphere and maybe have a major impact on the global climate of Earth. The duration of solar minimum may also have an impact on Earth's climate. During solar minimum, there is a maximum in the amount of cosmic rays reaching Earth. There is a theory that cosmic rays can create nucleation sites in the atmosphere, which create cloudier conditions. Meteors, a component of space weather. The meteors cause interference to high-frequency radio systems that makes it difficult to sort out the desired echoes due to aircraft. Doppler high-frequency radar can suffer damage during times of intense meteor activity. It is possible that the meteoroid itself may produce direct damage to a satellite. This was the largest source of concern in the early days of space exploration. This threat may increase dramatically during certain years. The Hellenic meteor shower, which occurs around November 17 each year, increases 1,000-fold every 33 years. Diseases of astronauts. Space radiation can also cause radiation sickness that results in nausea, vomiting, anorexia, and fatigue. They could develop degenerative tissue diseases such as cataracts, cardiac, and circulatory diseases. Our planet's magnetic field and atmosphere protect us from harsh cosmic radiation. On this space station, astronauts receive over 10 times the radiation than what's naturally occurring on Earth. Above Earth's protective shielding, radiation exposure may increase the cancer risk. It can damage the central nervous system. The food is bombarded with space radiation. Forecasting space weather. The solar radiant flux at 10.7 centimeters is an excellent indicator of solar activity. The F10.7 correlates well with the sunspot number. The F10.7 index has proven very valuable in specifying and forecasting space weather. Ultraviolet emissions that affect the stratosphere and ozone also correlate with the F10.7 index. This measurement can be made accurately from the ground in all weather conditions. Sunspots group are visible by ground-based observatories. This daily sunspot analysis and classification is submitted at the end of each day. The official sunspot number forecast is provided by the Solar Cycle Prediction Panel, representing the National Oceanic and Atmospheric Administration, the International Space Environmental Services, and NASA. The official daily and monthly sunspot numbers are determined at the Royal Observatory of Belgium. So today we focused on the impact of space phenomena in a biological, technological and atmospheric level. Space weather research is of major importance in order to understand fundamental issues of our past. Moreover, new theories claim that the inversion of Earth's magnetic poles 42,000 years ago effectuated the decrease of the magnetic field which protects our planet. Tremendous impacts on climate and dramatic influences, with the milestone example of the Neanderthals' disappearance. Consecutive solar storms in an ice age are considered as the creation reason of DNA and consequently the appearance of life on Earth. I thank gratefully the Greek Society of Astronomy and Space for the transmission of scientific knowledge, and Professor Mr. Karagginas for the enlightenment in cosmological issues, my professor in the course Earth and Space Science from Johns Hopkins University, Mrs. Ellington, and the president of the Union of Greek Physicists, Professor Theodosiou, the astrophysicist, Professor Moussas, for his extremely didactic speeches, and the director of the Greek Museum of Meteors for the invitation, the chance, and the honor to participate in the milestone Asteroid Day, the researcher, Mr. Theodosiou. Thank you very much.
Είναι εξαιρετική, όπως πάντα. Σήμερα και στα αγγλικά είχαμε την τιμή να τα απολαύσουμε. Για όσοι το κατάλαβαν όλοι, η Γιασμίν εδώ πέρα έχει συνδέσει την παρουσίασή της αυτή για τον διαστημικό καιρό και με μουσική εκκλησιαστική που η ίδια παίζει σε εκκλησιαστικό όργανο. Έτσι, κάνουμε και άλλες παρουσιάσεις για το διάστημα, για τον Άρη, για άλλα θέματα. Μετεωροειδείς είναι στο διάστημα, μετεωρίτες όταν πέφτουν κάτω στη γη. Άρα στο διάστημα θα λέμε πάντα μετεωροειδείς ή αστεροειδείς αν είναι πολύ μεγάλα. Αν είναι από 100 μέτρα και πάνω, ο μέγεθος είναι αστεροειδής. Ό,τι είναι κάτω από 50 μέτρα, 20 μέτρα είναι μετεωροειδής. Θα μου πεις δεν το ξέρει κανείς αυτό. Αλλά για ένα που το ακούει και είναι ειδήμονας, θα το καταλάβει σίγουρα. Οκ, σε ευχαριστώ και εγώ πάρα πολύ.